The next quantitative forecasting tool we will be looking at is exponential smoothing, and it is another time series tool. Again, like moving averages, you are wanting to use more than one data point, or a couple in the case of the naive method with trend. So you want to look at more of the data available to you in the time series. And you are, again, like moving averages, probably not seeing any seasonality. You are not seeing any marked trend. So that basically you're trying to forecast a variable that moves around a level, an average value, and you are thinking that you will look at your past history and come up with a forecast for next time by paying attention, unlike moving averages, in which case you would be looking at just the past 3, past 4, past 5. You will look at all of your past data points and yet give the most weight to the most recent data point. And then the weight you give to each preceding data point in your time series is reduced exponentially, hence we call this exponential smoothing. The formula itself comes from that old maxim of success being a result of good decisions, and good decisions being a result of past poor decisions and learning from them. So what you do is you take your last forecast and adjust it by reacting to the error that was involved in that time period. So this looks a little ugly when it first comes up, but it's actually a very commonsensical formula. The forecast for time period t, given that we are using exponential smoothing with alpha as our parameter value, as our smoothing constant, is going to be equal to the forecast from the last time period, and we add back to it alpha. Alpha is the constant that you determine, you feed into the model. We add alpha times the error that we made in that last time period. So if we were overshooting the variable we're trying to forecast, then the error is going to be negative because forecast is bigger than actual, and this is going to pull it down a little. If we were forecasting a number that was too low, that in that case our error is going to be positive, and it is going to bring the last forecast up by alpha times that error. Alpha theoretically is a number between 0 and 1. In practice, your book says it should be between 0.1 and 0.5. Usually you don't use 0.4, 0.5 a lot. Typically it is between 0.1 and 0.3 in practice, and I will tell you why that is in relation to moving averages in a second. And how you decide which alpha values to try depends on your priorities, depends on what it is you're trying to forecast and what your goals are. If you want to be very responsive to changes in the market, so if last time was a high sale month, for instance, you want to definitely produce more this time in case it is also a high sale month, and similarly diminish production if last month was not so hot. Then you would pick a higher alpha value, feed in a larger proportion of your error back to your last forecast value, so that you have a more responsive, a more jerky, if you will, but a more closely correlated with the actual amounts forecast. If you instead have a production mentality where you say, I'd much rather be producing about the same amounts every time. I don't want to be having to change my capacity a lot every month. So I want to smoothen out my production. Then you probably would pick a lower alpha level, and you do come up with a quantitative forecast given past data, but it looks more smooth. Over here in this diagram, you can see in blue the actual observations, and then you look at them, you don't see a trend, you're seeing some movement for sure, but it's not seasonal, there is no cyclical pattern to it. So exponential smoothing seems like a good idea. And as you can see here, the alpha value of 0.4 is leading to your yellow line. You are reacting more closely to movements in the blue line, so it is more jerky, more ups and down. And then your alpha value of 0.1 is reacting less to your actual changes. So you end up with that pink line where it is all more of a smooth forecast. Now, I said we do not typically use very high alpha values in practice, and the reason for that is if your alpha is equal to 2 over n plus 1, then exponential smoothing with parameter value alpha approximates an n period moving average. So that would mean if instead of calculating exponential smoothing forecasts with alpha 0.5, you might just as well run a 3-point moving average. Similarly, the 0.4 alpha value exponential smoothing would give you results very similar to a moving average of 4 periods. So as you can see here, you probably would try out moving averages with 3, 4, and 5 periods to them. And then if it seems like your forecast is improving as you go from 3 to 5, you're probably not going to want to go into 6 period, 7 period, 10 period moving averages. You would instead switch to exponential smoothing with alpha values between 0.3 and 0.1 at various levels. And then you are going to pick the one that gives you the best results. What do I mean by best results? How do you typically set n in moving averages or alpha in exponential smoothing? Well, our old friends, the aggregate error measures, mean absolute deviation, root mean squared error, are still going to be our friends. And you're going to be computing these and going with assuming that your tracking signal is acceptable. You will be going with the parameter value that minimizes these aggregate error measures. Now, a couple of things that I would like you to think a little bit on. One is, what would happen if alpha is equal to 0? And what would happen if alpha is equal to 1? And I would like you to actually take out a piece of paper and work this out